Hey, welcome to my YouTube channel. In this video, I'm going to discuss Hermitian and Skew Hermitian matrices. So let's start the video. A square matrix A is said to be Hermitian matrix if A is equal to conjugate transpose of A. That is Aij is equal to conjugate of Aj for all I and j. A square matrix A is said to be Skew Hermitian matrix if A is equal to minus of conjugate transpose of A. That is Aij is equal to minus of conjugate of Aj for all I and j. If z is equal to x plus iota y, then conjugate of z will be equal to x minus iota y, and z will be equal to conjugate of z. It will implies that y is equal to 0. So z will be equal to minus of conjugate of z will implies x is equal to 0, which implies a purely imaginary number. Now for Hermitian matrix, putting I is equal to j, it will implies that Aii is equal to conjugate of Aii. Let Aii is equal to x plus iota y, which will implies that x plus iota y is equal to x minus iota y, which will implies that 2 into iota y will be equal to 0, which will implies that y is equal to 0. So all the diagonal elements of Hermitian matrices are real, and S is the collection of matrices in such that entry has been placed like this: ABC x1 y1 x2 y2 x3 y3 belongs to real number, represents all Hermitian matrices of order 3. Number of non-trivial entries on set of all Hermitian matrices of order n over field of real number is equal to n square. At each diagonal places, we require one arbitrary constant over R, and at the places above diagonal line, two arbitrary constants over R, and places below diagonal line requires no new arbitrary constants. So number of essential arbitrary constants required to write set of all Hermitian matrices of order n is 1 cross n plus n square minus n divided by 2 into 2 is equal to n square. Now for Skew Hermitian, putting I is equal to j will implies that Aii is equal to minus of conjugate of Aii. Let Aii is equal to x plus iota y. X plus iota y will be equal to minus of x minus iota y, which will implies that 2x is equal to 0, and it will implies that x is equal to 0. All the diagonal elements of Skew Hermitian matrices are either 0 or purely imaginary because of this. Now set S is the collection of matrices like this, in which elements has been placed like this: A, B, C, x1 y1 x2 y2 x3 y3 belongs to real number, represents all Skew Hermitian matrices of order 3. Number of non-trivial entries in the set of all Skew Hermitian matrices of order n over field of real number is equal to n square. For proof, refer previous proof. Now null matrix is the only matrix of any order which is both Hermitian as well as Skew Hermitian. Now the proof says, let A be a matrix which is both Hermitian as well as Skew Hermitian matrix. So A will be equal to conjugate transpose of A, mark this equation as number 1, and A will be equal to minus of conjugate transpose of A, mark this equation, and 2, mark this equation as number 2. Adding these two, you will get 2 into A is equal to 0 matrix, which will implies that A is equal to 0 matrix. How many matrices are there which are both Hermitian as well as Skew Hermitian? Every null matrix of any order is Hermitian as well as Skew Hermitian. So S will be the collection of 0 matrix of order n cross n such that n belongs to natural number. So the answer is infinite. Now conjugate of Z1 into Z2 is equal to conjugate of Z1 into conjugate of Z2, and conjugate of Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2. Now if A and B are Hermitian matrices of same order and K is any number, then A is equal to conjugate transpose of A and B is equal to conjugate transpose of B, and K belongs to complex number. So conjugate transpose of K into A will be equal to conjugate of K into conjugate transpose of A, which will be equal to conjugate of K into A. If K is real, then K into A will be Hermitian matrix, and K is purely imaginary, then it will be equal to minus K into A, and it will be Skew Hermitian matrix. So if K is real, then K into A is Hermitian matrix, and if K is purely imaginary, then K into A is Skew Hermitian matrix. A plus B is again Hermitian matrix. Conjugate transpose of A plus B will be equal to conjugate transpose of A plus conjugate transpose of B, which will be equal to A plus B, as A and B are Hermitian given. So if K1, K2 up to Kn are real number and A1, A2 up to An are Hermitian matrix, then K1 into A1 plus up to Kn An is again Hermitian matrix. So linear combination of Hermitian matrix is again Hermitian matrix. So now if AB is Hermitian, if and only if A and B commute with each other, conjugate transpose of AB will be equal to conjugate transpose of B into conjugate transpose of A, because the reversal law of conjugate transpose says conjugate transpose of AB is equal to conjugate transpose of B into conjugate transpose of A, and it will be further equal to B into A, as A and B are Hermitian given, so it will be equal to AB as A and B commute with each other. If A and B anti-commute with each other, then AB is Skew Hermitian. Okay, now see fourth proof. Conjugate transpose of A raised to the power n is equal to nth power of conjugate transpose of A, which will be equal to A raised to the power n. Now see this question. If A, B, C, D, E, F are Hermitian matrices in which any two matrices anti-commute with each other, then which of the following are again Hermitian? I have discussed the same question in symmetric matrix, so you can go through that concept and proceed to this question by yourself. If A is matrix of any order, then A into A theta is equal to A theta into A is always Hermitian, because conjugate transpose of A into A theta is equal to A into A theta, and conjugate transpose of A theta into A is equal to A theta into A. If A is any square matrix, then A plus A theta is always Hermitian. As the proof says, conjugate transpose of A plus A theta is equal to conjugate transpose of A plus A. It will be equal to A plus conjugate transpose of A. If A and B are skew Hermitian matrices and K is any number, then conjugate transpose of K into A theta will be equal to conjugate of K into conjugate transpose of A is equal to minus K into A. If K is real, then it will be equal to minus K into A. That will be skew Hermitian matrix. If K is purely imaginary, then it will be equal to K into A, which is Hermitian matrix. So real time of skew Hermitian matrices is again skew Hermitian matrices, and purely imaginary times of skew Hermitian matrices Hermitian matrix. So now see this second note. Conjugate transpose of A plus B is equal to conjugate transpose of A plus conjugate transpose of B, which will be equal to minus of A plus B, as we know that A and B are skew Hermitian given. So if K1, K2 up to Kn are real number and A1, A2 up to An are skew Hermitian, then K1 into A1 plus up to Kn into An is again skew Hermitian matrix. So it means the linear combination of skew Hermitian matrices is again skew Hermitian matrix. Now see this third property. If AB is skew Hermitian matrix, if and only if A and B anti-commute with each other, but if they commute, then AB is Hermitian matrix. Conjugate transpose of AB is equal to conjugate transpose of B into conjugate transpose of A by reversal law of conjugate transpose of two matrices. Now it will be equal to minus B into minus A. It will be equal to BA, and if they anti-commute with each other, then it will be equal to minus AB, which is skew Hermitian matrix. And if they commute with each other, then BA will be equal to AB, and then in this case AB will be Hermitian matrix. Now the fourth property says a raised to the power n is skew Hermitian or Hermitian according as n is odd or even respectively. Conjugate transpose of a raised to the power n is equal to nth power of conjugate transpose of a, which will be equal to nth power of minus a, which will be equal to minus 1 raised to the power n into a raised to the power n, that will be equal to minus a raised to the power n if n is odd, and in this case a raised to the power n is skew Hermitian matrix, and it will be equal to a raised to the power n if n is even, and in this case a raised to the power n is Hermitian matrix, as minus 1 raised to the power n is equal to 1 if n is even, minus 1 raised to the power n is equal to minus 1 if n is odd. Now see this fifth property. If A is any square matrix, then A minus A theta is always skew Hermitian matrix. So the proof says conjugate transpose of A minus A theta is equal to A theta minus conjugate transpose of A theta. It will be equal to A theta minus A, and you can write it as minus of A minus A theta. So A minus A theta is always skew Hermitian. Now see this comment. If P is any square matrix, then P theta AP is Hermitian or skew Hermitian according as A is Hermitian or skew Hermitian. And the proof says conjugate transpose of P theta AP is equal to P theta A theta P. It is equal to P theta AP if A is Hermitian, and in this case P theta AP is Hermitian matrix, and it will be equal to minus P theta AP if A is skew Hermitian, and P theta AP is skew Hermitian matrix in this case. Now see this question. If A is Hermitian matrix, then which of the following? Now see all of these options. You can clearly see that all options are correct, because null matrix is Hermitian matrix and skew Hermitian matrix as well as. So all these options are correct in this case, but if must be possible is asked, so we have to check for all the types of Hermitian and skew Hermitian matrices. So the first option says 2017 into A. So real times of Hermitian matrix is again Hermitian matrix, and the second option says but imaginary type of Hermitian matrix is skew Hermitian matrix. So the second option is incorrect. And the third option is again wrong, because imaginary times of Hermitian matrix is skew Hermitian matrix. The fourth option is again wrong because of this thing, and fifth option is again wrong because we know that real times of Hermitian matrix is again Hermitian matrix. So this is wrong. So the sixth option says imaginary times of matrix A is skew Hermitian. So we know that imaginary times of Hermitian matrix is skew Hermitian. So the sixth option is correct. See this question. If A1, A2 up to AN are skew Hermitian matrices in which every pair anti-commute with each other, then you can proceed to this question as in the manner as I proceeded in this skew symmetric question. Do it by yourself. Every square matrix A is uniquely expressed as sum of Hermitian and skew Hermitian. So let's suppose A be any square matrix, and further let that P and Q are Hermitian and skew Hermitian respectively, such that A is equal to P plus Q. Mark this equation as number 1. Now taking transpose conjugate both sides, we have conjugate transpose of A is equal to conjugate transpose of P plus Q, which will be further equal to conjugate transpose of A equal to conjugate transpose of P plus conjugate transpose of Q, which will be further equal to P minus Q. Mark this equation as number 2. From equation 1 and 2, we will get P is equal to A plus A theta divided by 2, and Q is equal to A minus A theta by 2. Here P and Q respectively known as Hermitian part and skew Hermitian part of A. They are also known as Hermitian and skew Hermitian matrices associated with A.